So this other word, shortest position time first, is another algorithm that is very similar to SCAN, except it's taking advantage of the fact that on some modern drives, the rotational delay and the seek time, average rotational delay and average seek time, are starting to become the same number. So most of our rotational disks, the seek time greatly dominates the rotational delay. But some very good performance, some of the more very expensive SATA drives are actually now getting where seek time and rotational delay are starting to come together. They're well within an order of magnitude. Sometimes it's a factor of 3 or less. Okay, and it turns out this effort to compress the seek time has really occurred, making these seek time and rotational delay come close together, has really only occurred, we've really only put a lot of effort into this since a different technology was invented. Does anyone know what that technology was? Solid state drives. Before solid state drives, rotational drive manufacturers did not have any competition. Okay. Well, you could have used reel-to-reel tape. Has anyone here ever programmed on a system that had reel-to-reel tape as its storage? If you spin the tapes too quickly, when you slow them down, they stretch. And your bits change size. So it turns out you can't optimize that. You have to go to an optimal rotational speed. It's really, really ugly. How many of you have ever used floppies as your primary storage? Okay. Floppies are light speed fast compared to magnetic drive. It's ugly. It's really, really ugly. So the latency on these, the buffer cache and write aggregation is important. When we talk about file systems themselves next time, we're going to talk about how this write aggregation and buffer cache can come together to give us a very high performance file system called the log structured file system. Okay. Well, some of the things that I want you to think about, I forgot to write this in here, but because of the buffer cache, we do write aggregation. And then, because we're servicing reads and writes out of the buffer cache, our communications with our disk become write dominated. Once we read a page in on modern systems, we have so many page frames that in general, it never gets booted out until our process exits. Okay? So that means that while our system is running, absent of us reading a new page, our I/O is only really just writes. So now the relationship with our disk is going to be write dominated. And it turns out, you guys remember, how many of you heard of Amdahl's law? Okay. Amdahl's law is interesting. It says if you want to improve performance, pick the part of your system where you spend most of the time. It turns out that once we start making disk drives primarily having to deal with writes, there's ways that we can optimize the writes that get us very, very big performance swings. Okay? That's where we're going to be working towards when we move into next week. So, solid state drives. Solid state drives are pretty cool. We're starting now, we're starting to be able to get computers that will have an SSD basically for their boot partition. We don't write to that partition very often. And some of the nice things about that is SSDs are all electrical. So they operate at the speed of electricity. Hard drives are electromechanical. So they operate at the speed of the mechanics. Also, hard drives have to have things like ball bearings, lubrication. Okay. Has anyone ever done work on their own car? Ever had a bearing break? What did it do to your performance? Okay, just not good. And it turns out that if we have things like ball bearings, we have things like friction. Remember physics? Okay, friction, does that help or hurt the lifetime of our part? It's going to hurt it, okay, because there's going to be this friction going back and forth.
But honestly, if you have that much friction, how long does your disc last? Because like I'm thinking, if this is moving at like the speed of light essentially, wouldn't that thing just burn up within hours?
Well, we're going to move the disc. This typically operate at about 15,000 RPMs. Okay, and once we get up and running, so did anyone here ever taken apart an engine or looked at diagrams for taking apart an engine? What happens is when the engine isn't running, when the motor isn't running, the lubricant all pools down at the bottom. But once it's up and running, it tends to form, if the lubricant's correct, it'll form a thin sheen, which will reduce the friction to the minimum amount. But it's still there. That's why oil breaks down and things like that. We'd rather have the oil breaking down and costing us $50 to change than the bearings breaking and costing us $3,000 to fix the bearing. But friction is still there. There is a lifetime. For almost all discs these days, the lifetime is until the bearings fail in some way. So when the bearings start to fail, it will introduce a vibration. And our disc head's floating 1/12 millionth of an inch off that platter. Do you think it's going to take much of a vibration before they touch? Does anybody know what we call it when the disc arm touches the platter? Who's ever heard the phrase head crash? Okay, that's what it is. And as soon as they touch, they just start dragging through the disc. And remember all that data that we just put down there that was so beautifully and carefully stored? Because we promised promised the user that eventually we'd put it there. We just destroyed it. Okay. So we have to be very, very careful in mechanical devices about mechanical failure modes. Okay? And I think most drives these days will say, oh, I'm good for 10 years. And that means if you turn it on and keep it spinning and never shut it off, it'll last for about 10 years before it wears out. How many of you just leave your disk drives up doing work all the time? Kind of doesn't happen. And what you might not know is if your disk that looks like it doesn't have any work to do, it's not going to sit there trying to hold that disk arm out there at 1/12 millionth of an inch. It's going to take it back to a reserved area of the disk. It's called the landing pad, and it will power down the disk arm and rest the read-write head. Because while it's holding it up there, what's happening is more wear is occurring on the system because no bearing is perfect. They're not perfectly round. So there's a vibration, but it's trying to hold that at 1/12 millionth of an inch. So they're fighting each other. That's another piece of equipment that's wearing out. Isn't this fun? Okay? So enter SSDs. SSDs are going to remove the mechanical portion. And because we don't have mechanical portion, what winds up being the transfer time for the I/O? Well, let's ask, what was it before for rotational disks? The time to do an I/O was what? We had that formula. I see three of you looking it up.
Oh, it's seek time plus rotational latency plus transfer time.
Yeah, so seek time plus rotational latency plus the transfer time. Which one was the smallest?
Transfer.
If we don't have a rotational disk, what happens to seek time? Goes to zero, doesn't it? What about rotational delay? It's gone. It goes to zero. So the cost of I/O is just the time to actually write the actual data, isn't it? That's what SSDs give us. Okay. At present, they don't give us better reliability. And that has to do with the materials that we use. We'll talk about that a little bit. But they're getting there. Rotational disks right now for things in about the 100 gigabyte to 1 terabyte range. Rotational disks, it's costing about 5 cents per gigabyte to make that drive. Now, our slides up here will say the book, because the book uses the number 65 cents per, actually gigabyte, I think, yeah, gigabyte for rotational and so we're using gigabytes for our measure. 5 cents per gigabyte for a rotational disk. The last time I checked on this was about a year and a half ago. It was 65 cents per gigabyte. So it turns out that SSDs are substantially more expensive because of manufacturing costs. I found several articles this morning in the trade press for the SSD industry that says because of an excess of what's called NAND flash, that the prices of SSDs should come down sometime during this year to below 10 cents per gigabyte. 5 cents versus 10 cents. This is starting to become a kind of a wash because it turns out we get more than a 2x speed improvement out of SSDs. Okay? So it's starting to become. Now, the numbers I saw a little bit earlier, I think I have that, no, I don't have that diagram, was saying that for a 4 petabyte drive, how many of you have a petabyte drive? Okay. Google has a lot of them. I did not realize that you could get 4 petabyte rotational disks and 4 petabyte SSDs. I would never have thought about a 4 petabyte disk, rotational disk at all. I never would have thought about that. But it's not like the platters are this big. They're still back around in the 4 to 6 category, 3 to 6 category, inches in diameter, inches in radius. Sorry, no diameter. So we're starting to see where SSDs are starting to become price point competitive with hard drives. Smaller SSDs are cheaper to make, smaller SSDs are easier to make because to make the big ones, we have to put them out in bigger and bigger chunks of the silicon that we'll have to do. So there's even a small crack in that could render that piece of silicon useless. So the smaller ones are much easier to manufacture than the big ones. So we're likely to see in consumer electronics, we're likely to see SSDs start to replace rotational disks. How many of you think this has a rotational disk in it? All right, it doesn't. It actually doesn't have an SSD, it has what's called flash. Okay, and that's flash. SSDs are made out of a particular type of flash technology. So there's pretty much made from the same technology. It's just they're made slightly differently. The flash that's in here is much slower than an SSD. So it's much closer to main memory speeds. Okay, SSDs, we expect them to wind up being right at main memory speeds here almost any day now, like sometime in the next 2 years. In which case, the delay of going to the disk might be, over going to main memory might be 0. We might be moving the bottom of the pyramid up. Okay, this gets really cool. So, SSD. There are a couple of things that go on with SSDs that are currently keeping them out of currently keeping hard disk drives alive. All right, the hard disk drive manufacturers are either busy off converting to SSDs or busy off putting commercials out there telling you how bad SSDs are. Those are the two things that they're doing. Does anyone read any of the computer industry trade stuff, Computer World, or any of that kind of stuff? You can tell whether or not the person that wrote the article, which industry they're favorable for, by which statistics they use. If you go out there and you go like, oh, SSDs, oh, these are so great, they're so wonderful. But it turns out they're really sucky, and it'll be years and years and years, and so they've fallen on the bandwagon. They go, it's bound to the inevitable, but they want to keep SSDs around for a long time. And I like to say that's a reporter who has stock in Maxtor, which is one of the disk drive manufacturers. If they have stock in a company that makes SSDs, then they tend to promote the SSDs. Okay, but I would do the same thing if it was in my financial interest. So SSDs have a particular set of problems that is recognized recognized, has been worked on. Some of the major improvements in the area of SSDs have come about because of the authors of the OSTEP book. This is where they do a lot of their research, SSDs and file systems. When we get to file systems, we'll see that, that there's one called the log structured file system, and it makes entire use of your device. And this is how SSDs are organized internally for the following reason. In order to store data, I have to turn circuitry on and off. And circuits are made, for better or for worse, out of real-world material. And it turns out that there's only so many times you can turn, can turn something from a 0 to a 1 or back to a 1, or even just write a 0 over the top of an old 0. There's only so many times you can do that before the material will no longer hold a charge. Okay? And this is why we have alternate tracks on our hard disks and things like that. So if something fails, some sector fails, we can just move the data to a different sector. The problem is called bit fatigue. And you'll see this written of a lot around SSDs. I'll talk about the bit fatigue problem. I'm here to tell you that rotational disks also have bit fatigue. We just never talk about it. All right? It's been so many years since we've optimized around that. Even though they still have bit fatigue, nobody really mentions it, except of course for the SSD manufacturers. The hard drive manufacturers and their friends will never mention bit fatigue. SSDs, if you're always writing to the same location, think about this like a configuration file. You're always reading and writing it. Okay? You can only get so many reads and writes out of that bit before it fails. In the disk world, the hard disk world, you can have a sector fail. Worst case, a track fail. Right? And those relatively small. In SSDs, the chunks of silicon they use are quite a bit bigger. So if you lose one of those, you're losing a greater percentage of your storage. But it turns out that we can work with this by doing what's called wear leveling. And wear leveling is a really cute trick. What we do is we don't write the data back to where it came from. What we do is we say if we need to write that data, we'll write it someplace else and then update our inode and say that's where it's at. Okay, the log structured file system, it'll be a checkpoint region, but the concept is very similar. What that means is that over time, we will spread our writes completely over the disk fairly evenly. So that means that the lifetime on our disk before the mean time to failure is not worst case performance of always hitting this file, but average across the entire disk, which is substantially higher than going in and hammering one location over and over and over again. It says before, how many people have you defragged your disk? Okay, press your disk drive. Okay, that pushes all the data into one region of your disk, so you don't use your whole disk, which actually reduces your lifetime. But it improves your performance because it's a smaller seek time. Okay? How many of you are like here, well, then maybe I don't want to compress my drive. Okay. It turns out it's a personal choice at this point. We do not, back 20 years ago, we would schedule our disk to defragment itself a minimum of 1 time per week, even on personal computers. We're writing maximum 10 megabytes on a 250 megabyte drive. But the performance is so bad, we want to keep compressing it or defragmenting it. Okay, we really don't need to do that anymore. But when you have rotational drives, particularly lower cost ones, they still recommend doing that because it will give you a noticeable improvement. But it will make the bit fatigue problem worse because you'll be spending all your time in one portion of your disk. It's a trade-off. There is no winning move on this particular approach.
Would that mean that bigger drives would last longer because you have more space to spread?
That's the theory. The theory is that the more tracks you have, and if you're doing wear leveling, the more tracks you have, the less you visit each track. Therefore, the less you visit each bit, therefore you improve the mean time to failure of your device. And that is a big factor. I mean, in hard disks, it's starting to become, it used to be, till about 15 years ago, the bigger the disk, the harder they were to manufacture. And they were really hard to manufacture. Okay? But now they're trivial to manufacture. The actual material side of it is really well known, well understood. I have a friend who has a company in LA that he actually grows the silicon that they turn into the disks. Okay, he makes what are called wafers. And so now it's, you know, making something that can hold 1 terabyte is not terribly more expensive than something that can hold 100 gigabytes. It's an incremental cost as opposed to a doubling. It's a very small increment. So it turns out that, and then because of that feature of better wear leveling, if we're using something like the log structure file system, we can get disks that will last 10 years easy. Okay, even like in a Google File Center or AWS, something like that. So disks themselves are getting very, very reliable, and it turns out that still currently the bit fatigue numbers on SSDs are still, they'll wear out a little bit faster than hard drives. But that's one of the areas, reliability, where our authors work. And the last I heard from them, by the way, Professor Karavanik, and have you guys heard of Bruce Irvin, who's been adjuncting for us? They both got their PhDs at Wisconsin and have worked with these two people. So they have good insight to what's going on. They can call them up on the phone and they'll actually answer their phone call. Right? I go to voicemail. But what happens is now you're starting to get highly reliable numbers for reading and writing individual bits.